All right, let's dive right into this explainer. Today, we're exploring an absolutely mind-bending paradigm shift in computational geometry and distributed systems. It's known as the OMI protocol, and it basically rewrites the rules of reality for software. How? By completely eliminating mathematical constants as foundational truths. Seriously, if you've ever had to deal with floating point errors breaking your code across different machines, you're definitely going to want to pay close attention to this.
Here's our roadmap for today. We'll start with the problem with constants, move on to geometry as incidence, then cover the four authorities, the concept of the universal receipt, and wrap up with why determinism actually matters.
Okay, section 1, the problem with constants.
So think about the classic way we represent a vertex, just a simple coordinate tuple, right? X, Y, and Z. It's the old way. It's how pretty much all computational geometry starts today. But there's a massive hidden problem here. When a length or an angle is computed using arithmetic over those coordinates, you're essentially importing floating point approximations. So machine A might round a decimal just a tiny bit differently than machine B. And boom, suddenly your consensus is completely broken. The protocol is basically trusting a rendering approximation before it's actually validated the underlying mathematical relationship.
Which brings us to a crucial question. When a system accepts a floating point projection as the ultimate truth, what is the actual authority of that value? I mean, for a video game renderer, it doesn't really matter. Close enough is good enough to just draw a pixel on a screen. But for a deterministic protocol, like a distributed ledger or a decentralized network trying to agree on an exact state, that close enough answer is completely insufficient. If your protocol accepts a geometric fact just because some floating point calculations as it's true, well, you've just made the projection the authority.
The OMI protocol systematically dismantles this whole flaw by splitting constants into two entirely different categories. First, you have protocol constants. These are stored values treated as the absolute authority. That's the old way, and OMI completely eliminates it. Instead, OMI uses projection constants. So famous constants like pi or the golden ratio, in this system they are strictly projection constants. Their values produced only after a relationship is validated, and they're used purely to display or measure things. They have absolutely zero authority over the protocol's state.
Moving right along, section 2, geometry as incidence. Before we go any further, let's define exactly what we mean by incidence. In OMI, incidence means we're focusing structurally on what a point connects to. It's a finite, exact relation among points, lines, and faces. We aren't looking at a location in continuous floating point space anymore. We're creating a flawless, perfectly checkable relationship. Think of it less like a GPS coordinate on a map and more like a social network. It really doesn't matter where the node is drawn, it only matters who the node is actually connected to. Classical computational geometry pretty much always starts by asking this fundamentally flawed question. Where is this point? And the second you ask where, you immediately force the system to invent a grid, right? You have to invent coordinates and you have to import all those messy decimal approximations just to plot that point. But OMI changes the paradigm entirely. Instead, it asks, what is this point incident with? Like, what does it touch? What are its exact relationships? In this view, a line isn't just some drawn segment, it's a specific relationship between points. A solid isn't a list of spatial coordinates. It's a balanced, totally undeniable incidence structure. By just shifting the question to, what does this connect to, we completely eliminate the need for floating point math at the foundation. Take a balanced incidence matrix for a tetrahedron, for example. There are absolutely no x, y, or z coordinates involved. It just states exactly how many vertices, edges, and faces connect to one another. Each vertex touches 3 edges. Each edge touches 2 vertices. This exact relation balances perfectly every single time. It's a deterministic, unarguable mathematical truth that can be instantly verified by literally any machine on the network entirely without needing a single spatial coordinate. And this brings us to a phrase that brilliantly captures the core philosophy of OMI. Constants are the projection receipts of validated incidence. What this means is that those beloved constants like pi, the square root of 2, or the golden ratio, they aren't rejected by OMI. The system isn't pretending they don't exist at all. They're just relocated. They basically become the shadow cast by a validated incidence structure. Pi only actually appears when you decide to take a validated structure and physically draw it as a circle on a screen. The math is the shadow. The incidence is the solid object casting it. All right, section 3, the 4 authorities. So the entire architecture breaks down into what are called the four authorities. Now, don't let the grand, slightly intimidating names fool you. These are just incredibly strict software layers. First up, OMI creates the citation, which is basically the claim or the address. Next is the tetragrammatron. Try to think of this not as some mystical term, but strictly as the validation rule checker. It's what proves the math balances. Then Metatron handles the projection. It takes that validated truth and draws it on a screen or maybe outputs an audio file. And finally, IMO is the carrier, the network or file system that actually transports the data. The coolest part? Each layer has zero power over the others. Let's walk through this step by step because it really translates the theoretical stuff into the operational. So step 1, the IMO network carrier receives some input from a user. Step 2, OMI parses this input as a geometric citation. Then, step 3, the tetragrammatron strictly validates the incidence matrix. And remember, absolutely no floating points allowed here. Finally, step 4, only after that validation is 100% successful is Metatron allowed to project that relation onto a screen. This flow ensures an absolute ironclad boundary between what is mathematically validated and what's merely drawn on a monitor.
Moving on to Section 4, the universal receipt.
Across all these distinct architectural layers, there obviously has to be a way to establish an unarguable source of truth, something every single machine in a decentralized network can agree on. Well, that truth is called the receipt. And it is exactly that, the ultimate proof of agreement. Once the tetragrammatron validates an incidence structure, it mints a receipt. This receipt acts as the durable, completely unarguable witness of a lawful relation. All the distributed peers can trust this receipt without question. There is literally no risk of floating point disagreements tearing the network apart simply because the receipt is based on exact relational counting, not continuous, messy approximations.
And because of this receipt, constants only appear downstream. Actually, let me say that again, because it's pretty much the linchpin of this entire explainer. Constants are not the cause of the geometry. They are the result of the validation. If your machine wants to render a sphere using pi, it must first have the universally agreed upon receipt. The rendering itself, and the constant used to do it, is totally optional and strictly local to your machine. The receipt, on the other hand, is global and invariant. Finally, Section 5, why determinism matters.
So you might be wondering, why does this strict mathematical determinism actually matter to you as a software architect or a decentralized app builder or an AI developer? Why should you even care about incidence geometry? Well, because it scales beautifully into secure, real-world human and AI collaboration. Since OMI separates validation from projection, it enables incredibly strict role and repo-based access control, or RRBAC for short. Roles define exactly who acts. Scopes define exactly where they can act. Validation is mathematically checked. But here is the real kicker. Absolutely no side effects, like writing to a database, triggering hardware, or publishing a file, can happen without a validated receipt. An AI agent can propose a change all day long, but it cannot execute a single side effect until the exact math of that proposal is validated and a receipt is safely generated.
To wrap things up, I want to leave you with a pretty provocative thought. If mathematical truths like pi and the golden ratio are no longer stored as authorities, but simply derived as shadows of verified relationships, what else in our digital world should we stop trusting as a primitive? Think about things like identity, ownership, and network consensus. It's a lot to chew on, but I really invite you to profoundly rethink how we validate reality in distributed systems. Thanks so much for joining me on this explainer today, and remember, keep questioning the constants in your code.